afternoon. My name is Frank Allgauer. I will be chairing this session, and it's my great pleasure and honor to introduce to you this evening's speaker, namely Dr. Ernst Scholtz from ABB, where he is currently the R&D strategy manager, directly reporting to the Chief Technology Officer. And in this role, he serves a very important purpose, namely he is the link between ABB R&D and corporate development there. Ernst has been born in South Africa, so for him was coming here, coming home. He got his bachelor's and master's degree from the University of Pretoria, and in fact he did his master's thesis with our IFAC president Ian Craig, and obviously he did that in a very good way because he received the award for the best student in engineering and the natural sciences for the whole of South Africa at that time for his performance as a student. Then he decided to leave South Africa, going to the US, getting his PhD at MIT, also in electrical engineering, doing his thesis with George Verghese on observers and controllers for power systems, which set also already the direction of his future involvement in research and work. Then right after his PhD, he joined the U.S. Corporate Research Center of ABB in Raleigh, North Carolina, where he was staying for 4 years. Then he was for a short half year outside of ABB, working for EPIC, Merchant Energy LP, on energy trading in Texas. And then since 2009, he was the global program manager for grid automation within the ABB Corporate Research, also based in Houston. And for that, he managed $14 million that he could distribute to other research centers throughout the ABB empire. For us academics, that's quite a number, I would say. Since only 1 month, he's in his current position, now back in Switzerland, in Zurich, Switzerland, at the current position. But Ernst has also always remained close contact to the academic community, so he has over 20 papers published in the area of power systems, smart grids, and this is an area that attracts a lot of attention at the moment. Ernst has received many awards for different things. I managed the award as being the best student overall in South Africa and the natural sciences, but altogether it was alone for his student time 5 awards that he received. And I also want to mention one more set of awards. I don't know how many. I think from his CV it looked more like 20 or 30 that he received for cycling. So he's a very sportive young man who has definitely no trouble coming up to the floor now and talking to us about the very interesting area of smart grids. Please, Ernst.
Good evening, ladies and gentlemen. Frank, thank you very much for that introduction. I'm not that young anymore, so it's great to be back here in Cape Town, the mother city. I was hoping for a little bit better weather, but it's nothing that a good South African wine can't fix. So today I'm going to be talking about the evolving electrical grid, from slow and passive to fast and active. So the idea here is that I'm not really going to venture down the route of talking about smart grids. I'm going to talk about a This is a very interesting topic, especially for power system engineers, but there's also a lot of opportunity for control engineers. And I hope I can keep you engaged. And lastly, before I move on, I just wanted to say thank you very much to Ian Craig for this invitation, because I think there is definitely more opportunity to introduce some power topics to the control community and vice versa. So with that being said, in order to help you optimize your capacity for concentration, so late during the day I give you this outline. So what I'm going to do is I'm first going to give you an introduction on ABB, then I'll move on and talk a little bit about the electrical energy supply chain. Then I'll highlight some of the drivers for grid evolution. then also some of the challenges we are facing. Then I'll move on to one specific topic that's quite interesting. It's on the integration of large-scale renewables using high-voltage direct current technology. Then I'll move on to the topic of high-voltage DC grids, highlight some of the challenges, and then move on to management and control of it. And lastly, I'll conclude with some takeaway points. So if we look at ABB, we're a global leader in power and automation technologies. At the end of last year, we stood at around 42 billion in revenues. We're about 145,000 people all around the world in about 100 countries. The numbers of employees have swelled a little bit over the past few years because of acquisitions, mainly in North America. For instance, we bought a software company dealing with utility space, and then also a software company providing solutions to mining industry. So if we look at ABB and its history, it was formed in 1988 through the merger of the Swiss Brown Bavarian Key and then the Swedish ASEA company. So I know there's a lot of Swedish control people in this crowd. One of my colleagues, Alf Isaksson, also from ABB R&D, is here. So if we look at these two companies, BBC and ASEA, they have a long history, both of them starting roughly in the late 1800s. So if we look at what we do, as one of the world's leading engineering companies, we help our customers to use electrical power efficiently, to increase industrial productivity, and to lower environmental impact in a sustainable way. How are we organized? We have 5 global divisions. So on the left, we start with our power products. So this is where we manufacture things like power transformers, circuit breakers, switch gears, and then we move on to power systems. And this is where we actually put all of these products together into a system and then also create the software that actually controls this big machine. So discrete automation and motion, this is the division where our robotics business is in, and I know a lot of you in the control community crowd is familiar with our robots. The other division we have is low voltage products, and this is where we create circuit breakers that would go in your house, for instance. Last division is process automation, and this is where we deliver DCS systems to the process industry, and we have various verticals where we deliver, like for instance oil and gas, mining, and even data centers, for instance. So you would find ABB technology all around you. You would find it in mining, you would find it in marine, even subsea. So you'll find it in agriculture, in food and beverage, in rail, you'll find it in renewable energy, and then also in your own homes. So ABB's got a long history of innovations. There's a lot of technology first that we have to our name. Just to highlight a few, turbochargers, for instance, in the 1920s. Then electrical systems for locomotives. That's also one of our main breakthroughs. Gas-insulated switch gears, industrial robots, and then also here ultra-high voltage. And then most recently, we have our invention, Frida, the friendly robot for industrial dual-arm assembly. And there are actually quite a few cool YouTube videos that you can go and look how these robots can work with humans in an assembly line. So how do we stay competitive? Innovation is very important to us. What we have in ABB is 7 corporate research labs, about 8,500 people in R&D in 30 countries at roughly 300 locations. Not all of these 8,500 people are in corporate research. Corporate research is a bit smaller. We're only about 750 people. So the rest of the people are actually doing research and development in the divisions. We annually invest about $1.5 billion, and we cooperate with about 70 universities worldwide. Some of them include MIT and Imperial College. So for completeness sake, I put up this slide. I think some of you in the control community have collaborated already with some of our research centers. But here you can see we have quite a nice geographical footprint. We have a research center in Raleigh, North Carolina, and that's the one that I joined in 2004. Then we have centers in Beijing and Shanghai, then in Bangalore, and then we have a few centers in Europe. For instance, we have a smaller center in Krakow where we do quite innovative piloting, and then the larger centers in Switzerland and Baden-Württemberg, and then in Västerås, where we have a big power lab. So now, after giving you a flavor of what ABB is all about, I'm going to move on to the electrical energy grid. And even though this is a comic, this is not that far from the truth, and I think people like Ian Hiskins can agree with this. It's true that in the developing world, there has been years of underinvestment in the infrastructure itself. So I like this comic because it shows you that anything that we're trying to do is creating a band-aid to keep the system up and running. But with the emergence or the social consciousness around smart grids, there's a lot more focus and attention on the electrical infrastructure, and that's been quite amazing to be in this field at this point. So what I'll start off with is introduce you the electrical energy supply chain. So we start off with having our generation, then we have our transmission systems, moving on to distribution systems, and then eventually delivering the electrical energy to the loads. So there's a lot of pieces of equipment in here, and to make it all work, we need different layers, and you can already see where this is going. But we need sensors to figure out what is the health of this system. We need actuators then also to act in case we find situations that it's not desired. Interfacing with these actuators and sensors, we have our protection and control layer where we sample and then also take decisions on the millisecond level. Then this interface again with our network management level. So on the protection and control layer, you need to act fast so you don't have all of the information of the complete system. But in order to make sure that you have a consistent picture, these levels of control need to interface with the network management. And this is where we focus on energy management and SCADA, making sure that the system operates economically. Then on top of that, we have the maintenance and service that the utility needs to complete. So it's maybe not real-time or mission-critical, but it still interplays with the network management. For instance, if you have a scheduled line outage, you need to reflect that in your network management system because your network model changed. So as similar with all automation triangles, we have a lot of data at the lower levels and only fewer data going up, but more information rich. And then at the higher levels, we take a few actions and then it propagates downwards. A challenge in power systems, though, is when we talk about data, a lot of the data is actually trapped in the field, so you can't really get it out to the places where you need to make the decisions. So a lot of smart grid effort actually focuses on how do you unlock this data. So if we look at electrification in general, it was voted by the National Academy of Engineering as the #1 invention of the 20th century. So it's a complex machine that you need to operate. And it's always reliability first, and then you focus on the economics. So what is a challenge in operating an electrical system? We don't have energy storage. So electricity can't be stored at will at large scale, so both time and location. So meaning that we need to balance the supply and demand And in order to do that, we manipulate the frequency and the voltage in the grid. So that's all fine and dandy, but what makes this picture even more complicated is nowadays with deregulation, there's this energy market out there. So you have a lot of people actually working or playing around here. So you have low generation and loads interacting with even virtual traders like hedge funds and banks playing in this energy market. So to elaborate a little bit more on this complex landscape that we as technologists in the power community deal with, if we look at the interplay of policy, regulations, and technology, what you can see here is on the left-hand side, if we look at the government, they have some concerns. They're interested in what's happening with the environment and the climate. They also want to make sure that for their people, the quality of life is good. So under some economic constraints, they then come up with their policies that they then feed to their regulatory bodies to make sure that action ensues to try and meet some of their objectives. But then here on the right-hand side, we have various technology options that could be used to try and meet the government's objectives. So for instance, if we talk about like in Europe, there's a lot of focus on having more greener sources in the energy mix. So obviously on the technology side, we have wind and solar technology, but then also we have power delivery technologies like high voltage AC, high voltage DC. So all of these play together to actually try to satisfy the government's objectives. So diving a little bit deeper into the European energy policy. So I think it's not news to anybody that in Europe there's a big drive to have more renewable energy. So the policy played a key role to get to a situation of today, where in Germany we have, when you look at the load, we have between 30 and 80 gigawatts of load. But yet, on the renewable sources, the solar sources is about 36 gigawatt, and these are mainly rooftop solar. And then wind, we're already standing around 34 gigawatts, and this includes offshore wind as well as onshore wind. So the point of this slide is just to say that it's quite important what's happening on the policy landscape in terms of what happens with this grid evolution. So it's not always just a technology push. So if we look at worldwide drivers that would dictate that we need a new electricity supply, we see growth is one of the big ones, where it's population growth and economical growth, especially in the emerging countries, like for instance in Africa. There's a huge need for electrification. Urbanization, less people want to live in the villages, they want to go live in the cities. And then one of the challenges we face is acceptance. Like, it's very difficult to build new infrastructure, especially in the developed world. Like building a new AC line probably takes years if it ever gets built. But yet it's quite well recognized that the importance of electricity is still growing by the International Energy Agency. So it's clear that we need to do better in terms of the supply and then also the actual applications of electrical energy. So a snapshot on what's happening across the world. So in North America, we have a power system that's it's a huge one, rapidly aging and more insufficient. The big smart grid focus in North America is, over the past few years, has been distribution automation, so making that system more intelligent, and then also focusing on asset management. In Europe, there's a strong push for renewables, and same thing in Asia, also strong push for renewables. I can spend probably another 44 minutes just talking on smart grids, but I'll try to kind of end it here. So this is a really old slide from ABB, circa 2009, trying to explain to the community how we see this transition from traditional grids to smart grids. It's clear that the existing power system today still has predominantly centralized power generation, one-directional power flows going from generation source down to the load. Essentially, you operate it so that the generation follows the load, and your operation is actually based on historical experience for the most part. And then as you move to, say, smart grids, what people kept on touting is that we'll move to centralized and distributed power generation, and it's clear that this is already happening. For instance, 36 gigawatt of distributed solar in Germany. It's clear that renewable power is here to stay, and what we're seeing, because this distributed energy resources is installed in the distribution network and not, say, in the transmission network, these distribution networks were designed very radially. So what you find is that now all of a sudden the flows have reversed. So it was designed for flow going from higher voltages to lower voltages, but now it actually goes back into the transmission system. So it's clear that what we do in the future is going to rely on operation based on more real-time data and more advanced control. So what I'll do next is I'll jump into the integration of large-scale renewables. And if you look at the potential that you can derive from the prime energy sources, like for instance here, the wind potential, it's not located, or the best locations is not where the energy is actually going to be consumed. For instance, here in Europe, you see that's where your load centers are. So with this location mismatch, it's clear that what we're going to need is some longer transmission distances. So currently, if you look at what we have, is you have generation plants built close to your load centers, so your transmission distances, and we can probably argue on what the exact numbers are, whether it's 50 or 200 kilometers, it could be a little bit more. But going forward in the future, if you want to access remote renewables, like for instance solar here in Africa or wind up in the North Sea, then you're going to need much longer transmission distances, and we're talking 1,000 kilometers plus. So we're not the only people coming up with plans and visions like that. There are other organizations echoing the same sentiments. For instance, Friends of the Supergrid, Desert Tech, like bringing solar from the Sahara into Europe. So these visions are nice and dandy, but in the end, there's still a lot of technology that needs to be developed to realize these visions. Talking about renewables, it's inevitable that I bring up this slide. I think this one is quite an old slide used by many people in ABB, elaborating on the variable output nature from these renewable sources. So if you try to use renewable energy in your operations, first and foremost what you're going to try to do is predict what the output is going to be. Quite similar to what you would do with trying to predict what the load is going to be so that you can use it in your planning and your dispatch on a daily basis. But your models are not going to be perfect, so there's always going to be some kind of prediction error. So you can try to create better models, but that's a lot of effort, maybe some effort wasted. Another challenge for operating with renewables is sometimes the wind just disappears, and then what you see is a steep drop in the power. So that's what they call the steep ramp rates. And when you lose that power, you need to bring up another generator to compensate for that. And most generators don't have such steep ramp rates to come up online. And then the last problem is basic intermittency. For instance, if you need power during the day, but the wind only blows at night, then you can't really use this renewable energy for your operations. So in the end, what you do is you still use maybe non-green sources like gas, or less green sources like gas, or maybe even coal. So I already talked a little bit about Germany, but it's quite interesting to take a look at what the German wind and PV supply looks like in August 2012. And you can see that the volatility is quite large already, and apparently it's increasing. I've seen some new figures on this. like last night. So the point here is that the generation profile is more dynamic, and with that, it's clear that we need a more agile energy system. So more agile in the sense that we need to take decisions faster, and we need to be able to act faster as well. So what are some of the technology options in trying to bring renewable energy to the loads? So we have our traditional AC systems. So you have your AC line going from point 1 to point 2. And then you can also have technologies like high voltage DC. And there's two types. We have high voltage DC classic and high voltage DC light. So this, at least I was able to get one or two equations into this presentation. So this is number one. So this describes the power law, or the power transfer law, going over this transmission corridor. So I'm going to next talk about high voltage DC. And this is a very exciting technology area, one that I've experienced a lot of breakthroughs over the past few decades. The most recent one is the announcement of a cable system that's been proven by ABB, which is at plus minus 525 kilovolts. And with that, you can transfer like 2.6 gigawatts just on a pair of cables. So we are introducing this technology at Seagray in Paris this week. So it's also good to look a little bit at the history. You know, I think a lot of the power engineers have heard of this story, the Battle of the Currents. So this was in the early days of electrification. The technologists had two competing technologies they needed to decide between, AC or DC. And distilling it down to what are the pros and the cons, the reason why AC won out is because of the ease of voltage transformation using the transformer. And then also, when you look at the waveforms, it's also easier to interrupt any fault current that might happen because you have a zero crossing. So imagine this being a fault current flowing in your system. Once you get to the zero crossing, what you do is you open up the contacts, and then it's an easy break of the circuit. Whereas on DC, obviously you don't have that zero crossing, so it's much more difficult to break any of those fault currents. So at the early days, there were a mix of AC and DC grids operating, but in the end, all of the DC grids were kind of decommissioned. There was some interesting tidbit that in a K.I.T system in New York, they only recently switched off their last DC circuit, maybe a few years ago. But with that as a backdrop, and as we started to interconnect systems that were more distant, and we started to increase the voltage level of the transmission network, it was clear that AC technology had some limitations. So over here we show the 3 zones. But as you can see, as you increase the length of transmission, the actual capacity quite drops down. So you have various things like a thermal limit, you have a voltage stability limit, you have an angle stability limit. But then if you look at HVDC, there you're kind of independent of the transmission distance, making it ideal for long distance transmission. So ABB has been in HVDC research for a really long time. So in 1954, we demonstrated the first HVDC link going from mainland Sweden to Gotland. And most recently, this is one of the technology milestones where we do transmission over 2,000 kilometers at 8 gigawatts at 800 kilovolts. So if we take a look at these kinds of HVDC systems, we have 2 classes. We have HVDC Classic, which uses what they call line-commuted converters, and the internal switches for those are thyristors. And then you have HVDC Light, which is what we call voltage source converters, and there we use transistors or IGBTs. Here you can see some of the technology milestones, but up here we show some of the technology breakthroughs in these technologies. So you can see for the classic, innovation kept on going. And the idea was to raise the voltage and then also the capacity. For HVDC light, the main research focus has been on increasing the capacity, but then bringing the losses down. It's still a little bit more lossy than our classic offering, but it still shows a lot of promise. So here I show some of the HVDC projects for ABB. And the main reason for showing this is that just to illustrate that in this neck of the woods, there's also some projects ongoing. So we have a project in Namibia called the Caprivi Link, where we're using the HVDC light technology and the overhead line to transfer or to stabilize two weak grids. And then also we have the upgrade of the Cahora Bassa HVDC link that terminates just outside of Pretoria. So next I'll talk about HVDC grids. So up to this point, I've mainly elaborated on the point-to-point connections of these HVDC systems. So as a next step, and really to realize things, or these visions like they propose in Desert Tech, a lot of people are proposing to have an overlay DC system that sits on top of the AC system. So what we want for this HVDC grid is to have a system where you can operate independent of several disturbances and also in different operation modes, like connected to the AC system or separated from the AC system. Some of the benefits that are foreseen when you go to this grid structure, then instead of multiple point-to-point links, you'll reduce the losses, and even more so when you compare it to AC systems. Another selling point is that it will have a less visual impact, because normally when you install an AC system or AC line with a certain megawatt rating, then it takes up much more real estate than an HVDC system. And then an interesting thing that's also coming up in Germany is people are talking about repurposing AC transmission lines to become DC transmission lines. So it's nice to talk about DC grids and the vision that we have, but honestly there's a lot of technology challenges there. So for instance, in such a grid, you probably need the DC breaker. Then another question is, how do you control the power flow in this grid? How do you restore it if something happens? And then cables of higher voltages so you can increase the capacity. And then last but not least is, what are the rules and the regulations for this operation? Because what you can see is this is going to span continents. So now elaborating a little bit on why you would need a high voltage DC breaker. If we talk about this voltage source converter technology, when you have a fault in your DC system, this voltage source converter behaves like a diode breach, and this fault current grows uncontrollably. So the only way that you can get rid of it right now in a point-to-point link is, if you don't have DC breakers, is to disconnect this AC breaker and then de-energize the complete system. But now the question is, what if you have multiple links or a grid? Do you want to bring the whole grid down just to clear the fault? And we definitely don't want to do that. What we want to do is isolate faults that occur and then keep the rest of the system up. When we say isolate it, we want to achieve this within like 5 milliseconds, because we're talking about a lot of energy being transported on this infrastructure. Additional benefit, once you isolate these faults and you remove the bad part in this grid, is that the converters that are not delivering or contributing to power transfer, they can still be used to help and control the AC grid. So that's what we call the STATCOM operation. So in 2012, ABB introduced the first hybrid high voltage DC circuit breaker. And I'm not going to walk you through how this operates, but It's hybrid in the sense that it has a power electronics branch, and then it's got a mechanical branch. The mechanical branch is what we need for low losses in normal operation. But then we need the power electronics branch to really help with the fast disconnection. So this innovation was recognized by MIT Technology Review in 2013 as one of the 10 breakthrough technologies. And it actually labeled ABB as one of the 50 disruptive companies in 2013, which is a nice distinction for a company that's been around for over 100 years. So now with establishing that one of the key building blocks for such a grid is available, a question posed to power system control guys like myself is, how would you operate such a grid that's now connected to existing AC infrastructure? And we came up with some of the functionalities that might be needed, and here it's plotted against how fast we would need to act, and then also what would be the geographical extent of the actions you take. And to some of the power system control engineers, you might find a lot of these bubbles over here looks quite similar as what we do in AC systems. And that's true, because what we try to do is map the philosophy from AC grid control to, say, DC system operation. So having talked about DC faults, and the other one that we've worked on here is on DC protection. So in this module, you want to first find out, is there a fault, and then what kind of fault is it? Like, for instance, is it on an overhead line? Then the question is it a permanent or a temporary fault? So if you need to act within 5 milliseconds, that gives you indication that the requirements on this DC protection is quite hard to meet sometimes. On the other extreme, we also need to focus on how do you plan the system and make sure that it can operate with the existing AC infrastructure. And then here's some in the middle. This is where we focus on the economic operation of this grid. So trying to map this to a control structure, we used a hierarchical one, or proposed hierarchical one. And this is what we came up with. So we have our primary level controls, so the converter controls, primary controls, high level controls, master controls, and then our SCADA energy management system. So what we have here is, I show one AC system over here, another AC there, and a DC system there. So these various control levels focus on different phenomena to control. And I think that unfortunately it's quite difficult to read. But here on the primary controls, this is where we look at milliseconds and local phenomena. Here on the dynamic stability, we're looking at seconds, and this is system-wide phenomena, like even on continental scale. And then schedule tracking and restoration, that's on second to minute, and it's regional and system-wide. And then the economics is more on the minute to hour, and that's also very system-wide. So we proposed this scheme, and we also discussed it with others in the power community. And it was actually accepted 2 years ago at the CIGRE conference in Paris. So it's important that it gains acceptance, because in the end everybody might need to have a similar type of structure to make the whole system interoperable as you go forward. So for the remaining of the talk, I'm going to dive a little bit deeper into dynamic stability and control of dynamics in power grids. So if we look at just a very simple power system, so here I'm showing a hydropower plant. So we have the dam, the water driving the turbine, and the generator creating the electrical power that we deliver to the load. So this describing the behavior of the system, or the dynamic behavior of the system, we use the swing model, which is essentially Newton's second law of motion in rotational format. This is quite an elementary system, just one generator, but now if you start to think about interconnecting more than one generator, then you get to a situation, and I'm using this figure as an analogy, where each cyclist over here is a generator, and then it's connected through chains or the grid. But now, when you think of a chain on a regular bicycle, the chain is quite stiff, but in a power system, these connections are very weak. So one of my colleagues who actually helped me prepare some of these slides, Mats Larsen, he's an expert in corporate research, he says you shouldn't think of chains, you should think more of rubber bands. So you can imagine that as each generator pumps out its power, and you have these kind of weak links, you are going to see a lot more, say, power oscillations between them. So focusing on a generator, like what I wanted to show here is more the stable operation region for each generator. So if you operate with your internal angle for this generator to be less than 90 degrees, then you're in the stable region. So getting back to this stiffness of these springs or this change between different generators, when you operate at a power transfer of roughly there, then that stiffness of that chain you find through the gradient at that point. But obviously, as you move closer to higher power transfer, then this gradient becomes less and less. So the system becomes weaker and weaker, or the interconnections. So now thinking about how do we control power oscillations, and I'm bringing back this familiar slide again. You can see we have various technologies. You have technologies like flexible AC transmission system technologies. Over here we have something called the static VAR compensator, which uses also some kind of semiconductors in it. Series compensation as well, some semiconductors in it, and then some mechanical type of devices like phase shifting transformers. And then also things like high voltage DC, and then also energy storage can be used to control these dynamics. So I will not touch on all of these technology options. I'll just keep on going down the track of elaborating on HVDC. And so now, if we think about how can you use HVDC light to control the dynamics of an elementary power system. So over here, we have just the two generators. It's close to our single machine infinite bus situation. And we have our AC link and our DC link. So what we can see for systems like this is that you have a situation where you can have poor or even negative damping of these power oscillations. So obviously what you can see here is a situation where you have negative damping and then the system goes unstable. So, but through the use of this HVDC branch over there, you can modulate power much faster, and you can do even active and reactive power. And then through that, you can try to stabilize the system and get back to your stable equilibrium. But now, trying to extend this to more of the grid scenario, we first need to try to understand really what are some of these dynamics that we're dealing with. So we understand the dynamics on the AC side quite well. We know that's our go back. We know it's our swing dynamics that I introduced a little bit earlier, where we have our inertia of the generator, we have our input, the mechanical power coming from the prime mover, and some damping. But then on the DC side, what are those dynamics going to look like? So here we're dealing with electromechanical systems, but on the DC side we're dealing with electromagnetic systems. And looking into parameters from the field, it's quite nice to see that we do have a separation in these kind of dynamics. So focusing on the natural frequency for AC systems, for these power oscillations, we're talking sub 1 hertz. But then the dynamics on the DC side, we're talking about 20 to 60 hertz. Damping coefficients is also quite different. But this is still a quick back of the envelope type of calculation we did, because in real life we would actually need to model all of the controls, like the primary level controls, etc. So what we did is we moved and studied a little bit more of an illustrative power system. So it's still not very large, but it's enough to demonstrate the point. So over here, what we have is we have AC grid B and AC grid A connected through a DC grid. And just modeling the primary control on the DC converter sides, we were able to see through modal analysis that the dynamics do have a nice separation. But now the question is, that was what was to be expected. So what do we want to really do with this? So what we proposed is to, through taking the correct measurements and then also using this idea of power modulation, can we improve the damping in this combined system? And that's what we illustrate here, where we move some of our eigenvalues a little bit further in to increase the damping. And through design, what we get to is a stage where we actually mix the dynamics. So we have mixed AC and DC dynamics, and also this introduced power oscillation damping controller. So the point of this is, and when we look at what this looks like in the time domain, is that a situation where we see we obviously unstable, we can actually use this DC grid to kind of bring these AC systems back to a stable equilibrium. So you can view this DC grid as a powerful actuator for control of AC systems. So this is on top of all of the other benefits that HVDC grids can bring to the table. So second to last slide is really to talk a little bit about how we as ABB are moving beyond just theory and trying to put these things into practice. So all of those control functionalities illustrated earlier that's needed to manage this interacting high voltage DC and AC system that was devised in corporate research, we are now demonstrating this in a state-of-the-art hardware in the loop simulation center in Västerås, Sweden. So it's quite clear that ABB is committed to moving beyond just this theory and moving it to practice. And this is very important, actually, to have this functionality to illustrate how these systems could work, because there's no way that you can really sell this concept to a transmission system operator if you can't convince him first. So something like a technical paper is not going to do the trick. So we have people from ENSO-E and all of the big transmission system operators in Europe actually coming to visit in Västerås, and we walked them through the whole concept. We showed them the DC breaker, etc. But even after doing all of that work, it's still going to take time to bring about such a grid evolution. So I thought I was going to run long, but it seems like I'm going to run short. So I'll give everybody extra time for dinner tonight and maybe extra glass of wine. So I'll conclude here with some takeaway points. It's clear when we look at these electrical power systems or electrical grids that there's a lot of changes in full swing. We see renewable energy in Europe. Renewable energy is also big in the States. We see microgrids also popping up. But then for all of these changes that are occurring in this grid, there are various technology options that could be used. The one that I touched on tonight was high voltage DC, which is a very interesting one for the integration of large-scale renewables. Then moving to an HVDC grid as opposed to just multiple point-to-point links makes sense, or just using AC for that sense. It all makes sense because we'll get increased economics for it, reliability as well, but there are a lot of technology challenges. We have addressed some of them, we've solved some of them, but there are still others that remain. So it's clear that these challenges are not just confined to like the traditional primary equipment that we power engineers deal with, but it also touches on how do you operate such a combined interacting AC and DC grids. So stepping back and thinking just of AC grids as it is today, these are very large-scale nonlinear systems. There are some controls in them, but not that many, and they're also probably quite slow. So these AC grids by themselves are placed under a lot of stress when we bring in all of this renewable energy. So by using more things that have power electronics and semiconductors into them, like enabled power electronics enabled DC grid, we can act much faster and control the existing AC infrastructure, which is not going to disappear, in a much better way. And then lastly, it's clear that ABB is playing a key role in demonstrating the feasibility of technologies that can bring about grid evolution. So with that, I'll end the presentation, and then if you have any questions in the future, you can seek me out for the next 2 days. So, and thank you for your attention.
So, thank you very much, Ernst, for this very interesting insight in the future of power distribution, the power grid, and also what challenges and opportunity there are for the control field. As was decided generally for the World Congress, there will be no opportunity for direct questions and answers from Ernst. But as he said, he's around for another 2 days, and I'm pretty sure he is also willing to answer any questions that you may have right away when you just come down and ask them to him. So let me end this session by thanking Ernst again for this highly interesting presentation. Thanks very much, and I wish you all a good evening. Goodbye.